Welcome back to another episode of Mr. Findlay Plays Some Music and then tries to relate it to some maths. You're probably as surprised as I am that an episode 2 even exists, but here goes, and actually I think there will be a third episode, going crazy now. As a quick recap, in episode 1 we discovered that Mr. Findlay playing 3 notes does indeed count in music. We saw how notes and instruments are based on sine and cos waves. We found that instruments with reeds had substantially more complicated waves, which were sums of sine and cos waves, and those created those complex structures. And finally, obviously, we discovered that Mr. Findlay knows at least one flute tune. So, let's see where we can go from there. We're going to keep thinking about waves in a little bit of depth. Not those waves. Or that wave. Nope, not even ocean waves. Sound waves. Good old sound waves. Well, I promise that is all the pretty pictures that we're doing. Everything else, I promise, will be graphs. Now, we've seen waves from different instruments and different notes have different shapes. But what about a single wave? Can we change it to look different? Are different notes produced connected in some way? Well, that's the question we want to answer, and we want to look at whether we somehow have families of waves. No, sorry, promise, graphs, not pictures. Now, let's go back to the flute for a little piece, and this is one I like to call All by the Sea, but Nothing About Tides, where we hear two related notes, middle C and then treble C. These lie an octave apart, and we're going to see how they're connected. Okay, so there were our notes, and I've shown you kind of the waves being created, but now I've brought those two waves up here so we can have a look at what's going on with them. Now you hopefully can see the scale there. The scale is we're gaining every few little marks here, we're gaining 1,000th of a second, and it's exactly the same scale for our bottom wave down here. So these two are scaled the same. So let's put on a few lines to show us where the notes start and finish. So you can see I've picked out a single big little hump of the middle C, but we can see down here in treble C that it's actually doing that whole pattern for treble C twice in that same amount of time. And you can see it on the second wave and the third wave, and the shape's not totally identical, but it's pretty similar. So the main difference is that in treble C it's doing it twice as often as it is in middle C. Now, we've got a maths way of talking about that. If this is a sine x-ish kind of curve, okay, I am aware that this is not sine x because it doesn't have the perfect waveform, but it's not miles off being a kind of sine x curve, then this one at the bottom is like a sine 2x. It's been squashed by a factor of 2 in the x direction. So that squashing seems to relate to the fact that we are playing up an octave, and that is not accidental. Here the doubling of x relates to the fact we've gone up an octave, and you could see that with any other pair of notes that I could play. You would always double the number of waves per unit of time if we went up an octave. Physicists have a nice word for this idea of how many waves fit into a given time, and they call that the frequency. So what we've just seen is that every time we go up an octave, we double the frequency. We're going to draw a little picture of that now, where 0 is on our scale. We're going to plot middle C, and then we're going to plot a frequency that's double that, and double that again, showing us the 3 C's of the musical scale. So middle C, tenor C, high C. Okay, now looking at that, these sounded very even in how we were going up when I was playing them. They're going up an octave each time, same sort of feeling of how far up we were going. But looking at the diagram, they aren't equally spaced. And that is something quite interesting that we're going to think about in a minute. Now, before we do that, we might as well add all the other notes. So we're going to zoom in on the scale a bit just between middle C and high C, and we're going to add in all our other notes. I mean, for starters, before we even get to any of the maths, what were humans thinking when they were having tones? That's your letters going up with no sharp sign. You know, nice C, C sharp, D, D sharp, E, F. What the heck is that mess about? And then we've got it again at B, C, and we've got it again at E, F, and the higher B, C. Who knows why we've got these weird pairs of letters? And yet we've got other pairs with semitones in between. Ugh, yuck. We could just have had 12 named semitones. Who knows why we didn't? Anyway, more problematically, from a maths point of view, as we're stepping up the scale, it looks like our gaps start nice and even, but we can spot they're slowly getting bigger and bigger and bigger and bigger until if you look right up at the top end of our scale, our gap's definitely substantially bigger than down at the bottom end of the scale. So even across the first octave, those gaps are getting bigger. And that's a major problem, because that means that although it sounds like we're doing nice even notes, they're not evenly spaced on a frequency scale. So how can we figure out what those notes are actually doing and where they should actually fit? Well, the truth is that there is a lovely bit of maths that solves it. Of course there is. It's called logarithms. And a logarithm will have a base, a number that we're basing it on. And in this case, when we're working with music, we doubled our frequency to go from C to treble C, and doubled again to go up to high C. So we're working in base 2. We're doing some kind of doubling as we go. Now what a logarithm does is it solves this little equation, which is 2 to the power of what number gives us the frequency of that note. So what power do we raise 2 to get our frequency for any given note? Well, there's a nice button on your calculator that reverses that operation to solve that equation, because it would be a lot of trial and error to figure out the value for x, but the button on your calculator says log to the base 2 of whatever the frequency is, and that will return our value for x. Now if we plot those values for x on a line, all our notes to log to the base 2 are nice and evenly spaced. And that means we can actually evenly space out our notes, and we can plot them in a nice, neat way. Oh, finally! Ta-da! Maths rescues music, and we can all go home happy. There is one thing that I want to talk about before we go, though. Let's link back, to finish off, to that flute note that we played right at the beginning. And I called this a sine-ish wave. We had this kind of repeating pattern, which made it a sine or cos style wave, but we ended up with this weird tall peak and a short peak. And I want to show you mathematically what's going on there. So, here's a little maths model. I've made the equation of y equals sine x. Let's adapt that a little. So instead of having y equals sine x, why don't we do y equals sine x plus sine 2x? So add in an octave higher. Well, here we can see we've got a big bump, little dip, little bump, and then back to the bottom of the curve. So actually we can physically see what the flute is doing when we get that waveform, the flute is producing a note plus some noise from a note exactly 1 octave higher. Now, we actually had a second instrument that we were playing in episode 1, and that was a clarinet. And I said this looked a right mess. But let's see if we can do better. So, let's adapt further. We're going to add in a sine 4x, and we're going to add in a sine of 8x. Now, as soon as I do that, so there's my new equation. It's got all these frequencies, so a note, an octave higher again, an octave higher again. We can see that this begins to look like the sort of mess that we had when we were looking at our clarinet note, which is just absolutely lovely. We get this beautiful pattern that seems to mathematically match what we observe when we record the sound. Oh, you can't ask for better than that. But we are going to have an episode 3 because I want to talk to you a little bit about the 12-tone scale. Now, it's going to take a few days for that to come out, but there will be an episode 3 looking at why we have a 12-tone scale-ish, and why in those 12 semitones in the scale, why they fall where they do in terms of that kind of log scale that we saw. Also, if you hang around, I do play a little tune at the end of this video too. Hope you've enjoyed that and found it interesting, and look forward to seeing you on episode 3.